Welcome to lecture number 14 of chapter 4 series. In this video we are going to continue the exercise questions. So first question for today is exercise question number 4.12. The question is like this: the reaction between A and B is first order reaction with respect to compound A and zero order reaction with respect to compound B. Fill in the blank in the following table. Okay, so here our reaction is first order with respect to compound A and zero order with respect to compound B. Now from that you can make formula of rate of reaction. Now here a table is given to you. In that table different concentration are given to you. You can see experiment number, concentration of compound A, concentration of compound B, and for that experiment the rate is given to you. Now in first experiment the initial concentration of compound A is 0.1, compound B also 0.1, and for that experiment number 1 the rate of reaction is 2 into 10 raised to minus 2. Now from the data given to first order and zero order we can make formula for rate of reaction. Here you can see formula is written: rate is equal to K, that is rate constant, into concentration of A raised to 1. Why 1 here? Because reaction is first order with respect to compound A, and B raised to 0. Why 0? Because it is zero order reaction with respect to compound B. So compound A raised to 1 and compound B raised to 0. Now for first experiment you can see here all three values are given to you. Concentration of compound A, compound B, and rate, that three values are given to you. Only K is missing. So what you have to do here, for experiment number 1 concentration of A and B and rate is given to you. Put that value in the equation and find out K value. Now for other experiments, experiment number 2, 3 and 4, one value is missing. You can see in the table one value is missing. Now we have find out the K value. Use that K value and find out these three values separately. So in step second, for all other experiment use K value and find out other missing values. Suppose I am taking experiment number 2. In that we have concentration of compound B, rate value is also we have in the table. We have to find out concentration of compound A. K value we can find out from second step 1. So put that three values in the equation, you will find out concentration of compound A. Like that for other experiment also you can find out the missing values. Complete that example. Exercise question number 4.13. Now the question is like this: calculate the half-life of first order reaction for from their first order rate constant given below. So in the question the rate constant is given to you. You can see different rate constant is there. Now we have to calculate the half-life here. Half-life we want to calculate. So just use this formula. You can see For first order reaction, T1 half is equal to 0.693 divided by K. K value is given to you. For first case it is 200 second inverse, for second case it is 2 minute inverse, and for third case it is 4 years. So put the three values one by one in this equation and you will get the answer. Now exercise question number 4.14. The question is like this. The half-life of radioactive decay of 14C is 5730 years. An archaeological artifact containing wood had only 80% of the 14C found in living tree. Estimate age of the sample. Okay. So here in the question, radioactive compound is there 14C, and for that 14C the half-life is 5730 years. Now we found out a sample of wood. In that 80% of 14C was there, 20% was decayed. With time it decreases, so 20% it decreased and 80% is left. Now we have to find out the age of that sample. So what are the values that is given to? Only one value is given to T1 half, that is the 5730 years. Now any compound that is radioactive, they are the reaction for that compound is first order reaction. You have to remember this sentence very carefully, listen to it. Any compound which is radioactive, the reaction for that radioactive compound is first order reaction. So radioactive decay is first order reaction. So T1 half is given by T1 half is equal to 0.693 divided by K. Now we have T1 half here, you can see 5730 years. So we can find out K value from that. K is equal to 0.693 divided by T1 half. So K is equal to 0.693 divided by 5730 years inverse. Here inverse will be there. Now the sample that we found out that had 80% of C14 left, means 20% of C14 is lost here. Now for first order reaction, this is differential rate equation. So 1 by K value we find out, that we can put here. ln 100 for initial concentration, R0 means at 0 time the concentration will be 100%. So I have taken 100 here, divide by when we found out the sample, it has 80% of C14 left. So here I have written 80. 100 divided by 80 is equal to time t that we want to find out. Now this 5730 that will come on in nominator here, 5730 divided by 0.693 into, convert ln into log, so multiply it by 2.303 into log 100 divided by 80, that is 1.25 is equal to t. Now this division you will get 8268.39 into 2.303 as such into log 1.25, that is 0.0969. So this multiplication, this whole multiplication, you will get 1845.18 years. That is our required time. That is the age of that wood sample. Next question, question number 4.16. The question is like this: the rate constant for first order reaction is 60 second inverse. How much time will it take to reduce the initial concentration of reactant to its 1/16th value? Okay, so for the reaction, rate constant K value is 60 second inverse. So, and our reaction is first order reaction. It is given in the question only. The reaction is first order. So we can write T1 half equation. T1 half equation was okay. So for first order reaction, K is equal to 60 second inverse, that is given in the question. Now suppose initial concentration is A, small a, that is our initial concentration. Now final concentration, that is 1/16th of A, means A by 16, and time we want to find out. So same equation we are going to use here, differential equation for first order reaction, that is 1/k into ln r0 by r is equal to T. Here K value that is given to 60, ln r0 means initial concentration, that is small a, divided by final concentration, that is A by 16. Put that values in the equation, you will get the answer. Next one is question number 4.17. The question is like this: during nuclear explosion, one of the product of 90 SR means 90 strontium with half-life of 28.1 years, if 1 microgram of 90 SR was absorbed in the bones of newborn baby instead of calcium, how much of it will remain after 10 years and 60 years if it is not lost metabolically? Okay, so the question what it want to say is, during nuclear explosion, this product 90 SR, 90 strontium was lost, and half-life for that compound is 28.1 year. Now a newly born baby consumed it, only this much it consumed, 1 microgram. Now time passes, and within this time this 90 strontium will decay. So after 10 years and 60 years, how much of that compound will remain in that baby's body if the compound is not lost metabolically? Okay, so how much that compound is there after 10 years and 60 years in that baby's body, that we are going to find out. So first of all, what are the values that is given to us? T1 half, that is given to us 28.1 years. Now after 10 years we want to find out, so I have denoted it by T1 is equal to 10 years and T2, that is 60 years. Now this is also a radioactive decay, So it is our first order reaction. Every radioactive decay reaction, that is first order reaction. You have to remember that. So for first order reaction, T1 half equation is 0.693 divided by K. Now we have T1 half here, so we can find K value. So K value will be 0.693 divided by 28.1 here. Now for first order reaction, same equation is here. Differential rate equation, 1 by K into ln R0 by R is equal to T. Now we have T value here. We have initial concentration. Baby has consumed 1 microgram, that is our initial concentration, and time T value is also given to us. In first case, time T is 10 years. So put the values in the equation. 1 divided by 0.693 divided by 28.1 into ln 1 microgram was the initial concentration, so 1 divided by concentration of R is equal to 10 years. Now 1 by R, that is R raised to minus 1, so I have written minus 1 here, and this one 28.1, that will come in nominator now. So 28.1 divided by 0.693, other values are same here. Now this division is 40.54, and this minus 1 is in power of R, so that will come in multiplication. So here I have written minus log minus ln R. Okay, now convert this ln into log. So here in multiplication 2.303 will come. Now I am changing the side, so on other side it will be in division. Minus side sign is also changing its side. Minus sign is there, and this value 40.54, that will come in division also. So log R, if you calculate this whole, you will get minus 0.1071. Now we want to find out R, so take antilog on both sides. So R is equal to antilog of minus 0.1071. Now antilog of minus value is not possible to find out, so take bar here. Just add 1 in 0, so it will be 1 here, and if minus this value from 1000, so it will be 8929. Okay, so antilog of this value you have to find out. It will be 0.7814. So after 10 years, this much compound 0.7814 microgram of 90 strontium will remain in the body of that baby. Now same calculation you have to do for 60 years. Just take T is equal to 60 here. Other all values are same. Next one is exercise question number 4.18. Here the question is, for a first order reaction, show that time required for 99% completion is the twice time required for completion of 90% of reaction. Okay, so here our reaction is again first order reaction. Now we are going to calculate time required for 99% completion of the reaction. So suppose our initial concentration is 100. Now 99% of completion it is given to you, means reaction is 99% completed. So out of that 100, molecule, suppose 99 molecule is converted into product, so only one molecule will remain as such in reaction mixture as reactant. As reactant we have only one molecule now, so R1, that is one molecule, 100 minus 99, that is one molecule only. Similarly, we have to calculate time of 90% completion of reaction. Now for that condition, R2 is equal to 100 minus 90, so it will be 10 here. Now for first condition, R1 is equal to 100 minus 99, that is 1, and reaction is first order, so again here differential rate equation is that 1 by K is into ln R0 by R is equal to T. Now put the values in the equation. K value we don't have, so 1 by K as such, ln R0 means initial concentration, that is 100, divided by R, that is 100 minus 99 is equal to T value. Now 100 minus 99, that is 1, so 1 by K into ln 100 is equal to T. Now convert ln into log, so it will be 2.303 divided by K into log 100 is equal to T. Now log 100, that is 2, so here instead of log 100 I have written 2. So what is time t? Time t is equal to 2.303 divided by K into 2. Now same calculation for second condition, when R2 is equal to 100 minus 90. Same equation is here, differential rate equation. Now instead of R0 put 100 here, instead of R put 100 minus 90. 100 minus 90, that is 10, so 10 will be here, and 0 0 you can cancel out, so we'll get 1 by K into ln 10 is equal to T. Now convert ln into log, so 2.303 divided by K into log 10 is equal to T. Log 10, that is 1, so here I have written 1. 2.303 divided by K into 1 is equal to T. Now see equation number 1 and 2. This is our equation number 2. Here 2 is there, and equation number 2, here 1 is there. So by these two equations you can say that time required for 99% completion of first order reaction is twice the time required for completion of 90% of the reaction. Okay, that's it for today. Thank you.